Okay, in this video we're going to start section 7.5, multiple angle and product to sum formulas. This section's a little longer. We're going to do this over 5 days, so there'll be 5 videos for this 7.5, and in each video there'll be a little more opportunity for practice. So these multiple angle formulas. In this section we're going to study 4 other categories of trig identities. The first category is functions of multiple angles, such as sine of k times u or cos of ku, where k is just some number. The second category is squares of the trig function, such as sine squared. Third category is functions of half angles, like the sine of u divided by 2 or half u. The fourth category is products of trig functions, such as sine of an angle times cos of a different angle. You should learn these double angle formulas because they're used often in trig and calculus. For proofs of these formulas, see Proofs in Mathematics on page 583 of your book. So here's some of our formulas, the double angle formulas. If we have a scenario where we have a sine of 2 times some angle, we can replace that with sine of, or 2 times the sine of u times the cos of u. I like to think about it as, this 2 gets pulled out in front and it becomes 2 sine of just u. And when we do that, we create a cosine of u to go with the sine of u. For tangent, if we have tangent of a double angle 2 times some angle, we could replace that with 2 tan of just u on the numerator and 1 minus tan squared of u in the denominator. Now, just for a more numerical example, if this was, say, tan of pi radians, well, if that would be 2 times a half pi is equal to pi. So when we filled in the rest of the formula, we wouldn't want 2u or just pi. Here we'd plug in a half pi for this u and a half pi for the other u. Now for the cos of 2u, we have 3 variations of the formula. The first one is we can replace cosine of 2 times an angle with cos squared of the angle minus sine squared of the same angle. And if we take this sine squared here and replace it with a 1 minus cos squared and distribute the negative, we could also have a 2 cos squared of u minus 1. Or if we go back to that original, the first one here, we could replace this cos squared with a 1 minus sine squared, and then collect our like terms and get 1 minus 2 sine squared of u. So there are 3 different things we can plug in for the cos of 2 times an angle. 1, 2, 3. So let's see where we would use these. In example 1, it says solve a multiple angle equation. Solve 2 cos of x plus sine 2x equals 0. Now this looks kind of similar to stuff we've seen before. We got a couple of trig functions we're adding or subtracting, and it's set equal to 0. The usual strategy there is to factor the equation and then set each factor equal to 0. But right now there's nothing we can do with this. We can't factor it at all without our new formulas. So if we look at our equation here, this sine of 2x is new. That's something we haven't seen before. And we can look to this double angle formula. The sine of 2 times something is 2 sine u cos u. So this first term is going to stay the same, 2 cosine of x. Plus this sine of 2x I can replace with 2 sine x cos x. 2 sine x cos x. And that's equal to 0. Notice how that worked. This was the sine of 2x. Now it's just x and x in our replacement from the double angle formulas. Now it looks like something we've seen in the past. This was back from section 7.3. We have 2 terms separated by an add or subtract sign, and we have a common term in each that we can factor out front. And we can also, it looks like, pull a 2 out. We can pull a 2 out of each term. And we can pull out a cos of x. So when we pull 2 cos x out of this first term, there's nothing left, or just a 1 to hold its place. Plus, well, we factored out this 2, we factored out the cos, so all that's going to be left is sine x. So they have just a sine x equal to 0. Now we've factored the left side and set it equal to 0. Now we set each factor to 0. If I set 2 cos of x equal to 0, I can divide both sides by 2, and this is 0 divided by 2 is still 0. So we get cosine of x equals 0. And where does cosine equal 0 on the unit circle? Remember, the 0 or cosine is our x coordinate, so that's going to occur at x equals pi over 2 and 3 pi over 2. And then we take our second term and set that independently equal to 0. 1 plus sine x equals 0 means that sine of x is equal to -1. And remember, sine is our y value. Where on the unit circle do we have a y value of -1? Well, that's all the way at the very bottom here, and that happens at 3/2 pi. X would equal 3/2 pi. And notice we have a repeating answer. You know, we had 3/2 pi from the first term and 3/2 pi from the second term. We only need to list it once. And then to make our solutions for, because we weren't on a restricted interval here, you know, we have our pi over 2 plus 2 pi n. And then we have our 3 pi over 2 plus 2 pi n. See here in example 2, use double angle formula to rewrite the equation y equals 4 cos squared of x minus 2. Then sketch the graph on the interval from 0 to 2 pi. So what we have is 4 cos squared of x minus 2. What does that most look like on our double angle formulas? Let's see, we have, again, that was a cos squared. So anything without a cos squared we could get rid of. So which of these does it most resemble? Well, it looks a lot like this. 2 cos squared of something minus 1. We don't have exactly that, but what if we factored out a 2? If we pulled a 2 out of here, we'd have a 2 times the quantity. 2 cos squared of x minus 1. Now this matches exactly what we have in our formula sheet. So we can take that 2 cos squared minus 1, 2 cos squared minus 1, and replace it with the cosine of twice that angle. So we want to replace what is within these parentheses with 2 times the cosine of this angle. So we want 2 cosine of 2x. Well, excuse me, there's not supposed to be a 2 in front of it. It's not 2 cosine of 2x. Yes, that 2 is not supposed to be there. We replace what is inside these parentheses, 2 cos squared of x minus 1, with just the cos of 2x. We doubled that angle to a 2x, and we got rid of sort of the squared and the 2 and the minus 1. So here we have 2 cos of 2x. And they wanted us to also graph that over the interval from 0 to 2 pi. It's been a while since we've graphed a trig function. Hope we haven't forgot how. So we're going to need some axes here. And let's see our amplitude. What's the amplitude of this function? 2. So we're going to go from a high of 2 to a low of, -2. And they want us to sketch it over the period out to 2 pi. And we'll chop that in half to pi. And then I'll mark the quarter pies, but I won't label them. Okay, what's the period of this function? When will it complete a cycle? Remember, for sine or cosine, we find the period by taking 2 pi and dividing by the number in front of x. So 2 pi divided by 2 is pi. We will complete a cycle between 0 and pi, and another cycle from pi to 2 pi. And remember, cosine here, it's positive, so it will start on a maximum value, a peak, so to speak. And 1 pi later, we will be done with a cycle back at the next peak. In between there, we will have a valley right in the middle at ½ pi, and our x-intercepts will be in between those. And the next cycle, we're at a hill at pi. We will end 1 pi later at 2 pi at another hill. We will have a valley in the middle at 3/2 pi, and x-intercepts in between. So now we have our dots, we can connect them. Down into the valley, minimum value, x-intercept, peak. Oop, this is getting bad, but hang in there. There we go. So we solved it and sketched it. For practice, here are two problems, number 19 and 20. This is very similar to the first example, extremely similar. So pause the video, give those a try, and see how you do. Okay, let's give this first one a shot here. And we got a sine of 2x minus sine x equals 0. You know, at first thought you might, oh, can I factor a sine of x out? No, we can't do that. You know, this is an apple with a 2x and this is an orange with an x. Apples and oranges can't be factored out. But we can do something to make them look more similar. We can replace this sine of 2x with 2 sine of 1x times cos of x. And then we have this other term, minus sine x equals 0. And we see in each term we can factor out a sine x. So we can pull out a sine x, and what are we left with inside? 2 cos of x minus, we factored the sine x out, but we need a placeholder. We need a 1 to hold that sine x's place. Okay, now we factored it to two factors. It's set equal to 0, so each factor goes to 0 independently. Sine of x equals 0. Remember, sine is y values on the unit circle. So where does y equal 0? Right on the x-axis at 0 and pi. So this happens at x equals 0 and pi. And here we're just restricted to the interval from 0 to 2 pi, including 0, but not including 2 pi. Okay, and then our next term, we're going to set this equal to 0. So we're going to add 1 to each side and divide by 2. And we're going to get cos of x equals positive 1/2. Okay, where's cosine positive 1/2? Well, we check our unit circle, and we see that occurs at 1/3 pi, and again at 5/3 pi. Alright, in number 29, it says use a double angle formula to rewrite the expression. Okay, let's see our double angle formulas again. And okay, here they are. 6 sine x cos x. What do we have that looks the most like that? Well, anything squared, it's definitely not going to be, so we can get rid of all of these. Here's tangent with some tangents in it, and a squared, that's not going to be it either. So the closest we have is this right here. And what we are given looks a lot like the right-hand side. So is there anything we can do to our given problem number 29 to make it look more like this? Well, the only thing different is this 6. And we can break 6 up into 3 times 2 sine x cos x. Since that's just a big multiplication problem, you know, we can pull that 3 and that 2 apart. So now if we focus in on just this piece, this 2 sine x cos x, I can replace with the sine of twice this angle. So all of this becomes the sine of 2x. And we still have this 3 in front. So that becomes 3 times the sine of 2x. Okay, now a couple other practice problems. Kind of similar to what we just saw, but not exactly. In this exercise, find the exact solutions of the equation between 0 and 2 pi. And in the next one, use a double angle formula to rewrite this expression. So, let me grab our formulas here. Cos of 2x minus cos x. So here is what we want to deal with, the cos of 2x. Here's cos of 2 times something. We have our choice of things to replace this with. Since our other term is a cosine, we probably don't want to replace it with this. It does have a cosine, but this sine squared is completely different. We could try to get everything to be just cosines. So let's eliminate the first one. The last one for the same reason. We have a sine squared though, so we probably don't want to replace it with that. But this one here has a cos squared term and just some numbers. Here's a cos. That'll make it easier to factor. So let's replace this cos of 2x with this quantity. 2 cos squared of just x minus 1, and then we have this minus cos of x. And that's all equal to 0. Okay, what do we do next? Well, let's see. We have a squared term, a first power term, and some numbers. It looks like this could be a quadratic. And I'm going to rewrite it in descending order. My squared term first, my first power term, minus 1 equals 0. Can we factor this? Let's see here. What are the factors of 2 cos squared? Well, it's got to be a 2 cos of x and a cos of x. Our final term is a 1. The factors of 1 are 1 and 1. And we need the plus and minus signs to give our middle term a negative 1 cosine of x. So it's going to be 2x plus 1 and cos of x minus 1. Okay, now we set each factor separately equal to 0. So when we set this equal to 0, we're going to subtract 1 from each side and divide by 2. Or the cos of x equals negative a half. Here we're just going to add 1 to each side. The cos of x equals 1. Okay, on the unit circle, where does cosine of x equal negative a half? At 2/3 pi and 4/3 pi. And I'm not going to need the plus 2 pi n because we're still on a restricted interval just between 0 and 2 pi. And where does cosine of x equal positive 1? Well, again, on the unit circle, that's our x-axis, or x-coordinates or cosines. Positive 1 would be right there, so that happens at 0 pi. All right, number 32. Use the double angle formula to rewrite this. So this is kind of like the second problem we had, where's that? Right here. In this example, to make it look like what we had on the formula sheet, we factored out a 2. This is sort of a twist on that problem. What can we factor out of this to make it look like one of these? Well, a cos squared minus something, the closest is this. What would we factor out of this? Remember, there's a 1 here. What would we factor out of this to make it look like 2 cos squared of x minus 1? Or another way to think about this, it might be easier to see it this way. I have my term cos squared of x minus a half. How could I make this look like my formula here? Well, I could multiply this by 2, distribute that 2, and it would be a 2 cos squared of x minus 1. But if I multiply through by a 2, I've changed the equation. To balance out multiplying through by 2, I could also multiply it by its reciprocal, 1/2. So I haven't really changed the problem. It's almost like I factored out the 1/2. Because if I distribute, a half times 2 is 1 cos squared of x. A half times this minus 1 would be the minus 1/2. So it's sort of like we factored out a half, or that's exactly what we did. So now, how can we rewrite this a little bit? We can take what is in these brackets, this 2 cos squared of x minus 1, and replace it with just a cos of 2x. So we're going to have 1/2, and then inside the brackets we replace with the cos of 2x. 1/2 the cos of 2x, or you could write it as cos of 2x over 2 if you wanted to. The assignment for this section is 6 problems on 582.